Hi, my name is Shrestali, and today I'm going to talk about our work titled RadNet, Incident Prediction in Spatio-Temporal Road Graph Networks using Traffic Forecasting. This is a joint work with Matthew Wilkinson and Chris Cattell. Spatio-temporal forecasting is a critical problem for dynamic industrial environments such as transportation systems, supply chains, and mobile computational systems. And one such environment is the network of road traffic systems. And road networks act as systems that service mobile users where any incident could cause service downtimes. Here, road incidents take the form of anomalous events that deviate from expected trends, such as broken down or parked vehicles. Thus, the problem of incident prediction has gained attention specifically as a response to the growing populations, increasingly urbanized environments, and a drive towards more sustainable transport. Additionally, diagnosing the specific root cause of the incident, for example, the road where an incident has occurred, is crucial for informed remediation. Accurately forecasting and predicting incidents is challenging, mainly due to the complex spatio-temporal dependencies in long-term forecasting. In particular, the increasing number of sensors and devices in contemporary traffic sensor platforms calls for a more robust and scalable strategy. Moreover, the correlations between traffic speeds and queue lengths of roads with those of upstream roads or junctions requires a global analysis of the traffic network in lieu of a local one. Further, recurring incidents such as accidents or illegal parking give rise to non-stationarity, making long-term forecasting hard. To tackle this issue that we just described, prior work either uses knowledge-driven or data-driven methods, where the latter has been shown to outperform the former and hence considered as a de facto standard for traffic systems. Data-driven methods leverage deep learning models that learn to predict future system states using historic data. And state-of-the-art methods typically perform sequential inference of the form of spatial or temporal trends. For instance, if you see on the right, the architecture of DKFN from 6 Spatial 2020 independently performs temporal and spatial inference using LSTM and gated graph convolutions, and combines the two using Kalman filtering. Another approach called Graph WaveNet from IJCAI 2019 first performs temporal inference using temporal convolutions and then performs spatial inference using graph convolutions. What we realized is that fixing a particular sequence in terms of capturing these trends assumes them to be independent. For instance, inferring spatial correlations using graph neural network and sequentially inferring temporal trends using a recurrent neural networks makes the former oblivious to the analysis of the latter. And this limits their performance as we demonstrate later. To address the previously highlighted limitation of fixed sequences in spatio-temporal models, we propose a novel neural model that we call RadNet, which stands for Road Incident Prediction Network. It does this by explicitly inferring trends in both permutations and intelligently combining the outputs, facilitating an informed inference and consequently more accurate forecasts. Specifically, this network uses graph attention and transformer encoders to infer spatial and temporal trends and combines the outputs using a custom weighted skip connection. For further details on the implementation of this network, I refer you to our paper. Now that we have described the model, let me now throw some light on how we use this model for incident prediction. We study the important use case of utilizing a set of key parameters of a road traffic network to predict incidents or anomalies at a future time step. Such parameters or features include, say, flow rates, traffic speeds, and queue lengths, and characterize the state of a road traffic system. We decompose the incident prediction problem into one, forecasting the system characteristics at a future time step using historic spatio-temporal traffic data, and two, comparing the forecasts against historic averages as a baseline to indicate the chance of an incident at that time step. And this is applicable in the domain of traffic systems as they largely conform to periodic trends such as daily or weekly trends as shown in the figure. To visualize how this works, we first get a time series dataset from a road traffic network, which we use as ground truth. This dataset consists of temporal traces of the parameters such as traffic flow, queue lengths, and vehicle speeds for each of the nodes in the road traffic graph. For each time step, we use the parameters of that time step to generate a prediction of a future time step that may be 5, 15, 30, or even 60 minutes in the future. And we call this the prediction series. We also generate a time series of historic averages for each parameter based on the time of the week. So now that we have baseline, ground truth, and prediction, which are visualized through the figures in the bottom left, we now can generate residuals between the ground truth and the baseline, as well as the residual between the prediction and the baseline. And these are shown as green line plots on the bottom right. Now, using any standard dynamic thresholding policy, such as peak over threshold, we can generate binary anomaly labels. The predicted labels can be compared against the ground truth labels to measure the performance of a model. We compare RadNet against state-of-the-art models for spatio-temporal forecasting and incident prediction. We use multiple metrics for comparison. For incident detection, we use precision recall F1 score of the models for the predicted anomalies with respect to the ground truth anomalies, as we described before. For incident diagnosis, we calculate the hit rate and normalize discounted cumulative gains. And we calculate these metrics for two popular publicly available datasets. The first is MetRLA, which is collected from the highways in Los Angeles. The second is PEMS, collected from highways in San Francisco. And we perform experiments for 4 look-ahead times, 5, 15, 30, and 60 minutes. And these times indicate how far ahead the model can forecast accurately. And a higher look-ahead time in incident prediction corresponds to more time given for incident remediation. As you can see, the scores for the RadNet model are the highest across most metrics, across the two datasets, and for the different look-ahead times. However, we realized that the previously described traffic datasets cover only highway networks in United States, and the performance of models trained on these datasets may not translate to, say, European road networks. Moreover, the two datasets capture only speed data for highways, and there is a dearth of datasets that capture data for non-highway road networks where the traffic lights and, say, illegal parking may give rise to incidents not as common in highways. Further, the above two datasets lack other parameters of road networks such as queue length and traffic signals, and thus we present for the first time the RadSat dataset collected from a network of 24 sensors in the Radcliffe area in Greater Manchester, UK. And unlike the other two datasets, where only the aggregated speed readings are recorded, RadSat provides 7 features at each sensor, including flow rate, congestion index, and queue lengths. And comparing the RadNet model against the baselines for the different metrics, even for the RadSat dataset, we see that RadNet outperforms baseline for this data. Thus, to conclude, as part of this work, we present RadNet, a novel neural network to perform both spatio-temporal and temporospatial inference for road traffic networks. We also present a novel dataset called RadSat for non-highway roads. We demonstrate that RadNet outperforms baselines for two publicly available datasets as well as the RadSat dataset. Specifically, RadNet gives up to 8% higher F1 scores than the state-of-the-art methods. And as part of future work, we will investigate extensions to dynamically adapt RadNet in case of non-stationary graph inputs, such as when there are road or lane closures. Thank you for your attention. We have released the RadSat dataset as part of Zenodo repository. For any queries, please feel free to contact the authors. Thank you.